Hello everyone, welcome to AP Physics C Mechanics. This time we're talking about gravitation. And so we talked about gravity before in the forces unit. We talked about gravitational potential energy before in the work energy power unit. But this is expanding it beyond just the Earth and into basically the entire universe. And so we're going to start off with what's called Newton's universal law of gravitation, or just Newton's law of gravitation. And what that basically says is the force of gravity is equal to a value g, it's a constant, times m1, m2 over r squared. Let's break this down. G is a constant, the gravitational constant or universal gravitational constant, which is approximately equal to 6.67 times 10 to the power of negative 11 Newton times meter squared per kilogram squared. That's the unit for the gravitational constant. And the two masses, you're basically having two masses that have a force between them, and so you just multiply the two masses together, and r is the distance between the centers of the two masses. And so you can use this for basically anything, and in fact, if you plug in the values for Earth, for example, if you plug the Earth's mass here and the Earth's radius here, and just the mass, you keep this as the mass of any object on the Earth's surface, it simplifies down to F equals mg, where g is 9.8. And so the 9.8 comes from this equation. Now this is usually used with particles because, the radiuses of the particles themselves are negligible, but you can use it for big bodies too if you're given values. You just have to make sure it's from the centers and not from the surfaces. And so you should definitely know that. It's probably on your equation sheet too, but you should know that. Also, the force of gravity between the two objects are going to be the same because of Newton's third law. If you have a big planet and a small planet, or a big planet and a moon, the force of gravity is going to be the same. It's just the gravitational acceleration between them that's different. All right. Now, this is if you have two bodies. That's why there's M1 and M2. What if you have more than two bodies? So let's say you have like a 3-body system or a 4-body system. What it's going to be is just going to be the vector sum of all the forces of gravity. You calculate the force, all the forces acting on one particle, on the other particle, on the third particle, and then you just add up for each particle and you get the forces acting on each particle. Now, these might not always be the same because Newton's third law is only between these two interactions, and that might be different than these two, and so on. And so if you use this for multiple, you just add up all the vectors. And so this involves vectors, probably trigonometric calculations where you have sine and cosine. You might want to find this angle, find sine and cosine, and then add up the vectors. So not just scalar addition, vector addition. Be careful with that. Now, we've talked about gravitation near Earth's surface before. It's just F equals mg. But lowercase g, by the way, not uppercase g. That's different. But now let's expand it a little bit. Here we have F is equal to g times the mass of the Earth times the other mass over r squared. And like I said, we can simplify this into F is equal to m times ag. Ag in this case is similar to lowercase g. It's just we're going to specify the difference between them because ag is equal to the value g times the mass of the Earth over r squared. Now, ag is not always equal to lowercase g. It could be different. Lowercase g is 9.81. We know that. Ag can be different because, as we're going to learn in this topic, the value of the acceleration due to gravity is not the same everywhere on Earth. There's a few reasons why. One, Earth's mass isn't uniformly distributed. There could be mountains in one area, oceans in the other. It's the densities are different. The Earth is not a perfect sphere. It's kind of elongated at the equators, or bulging, and so that could cause a change. And then the Earth is also tilted. It's not perfectly straight up, so that's also something. The Earth is also rotating, and that's one thing we actually do have an equation to describe. This is basically the lowercase g is equal to the acceleration due to gravity minus omega squared times the radius of the Earth. Now, you might not need to use that equation, but it's good to know. Omega is the angular velocity of the Earth. Again, probably not going to use this equation, but you just need to know that the rotation actually decreases. The measured free fall acceleration is less than the gravitational acceleration due to the Earth's rotation. So few things you should know. Now let's talk about different types of spheres, and in other words, just certain situations. So let's say you have a point mass. We already know the formulas for that. And a system of point masses, we also know that. That's just Newton's law of gravitation and then the vector sum, like we talked before. Now, what if you have a solid sphere, like the Earth? If you're outside the solid sphere, again, we know what that equation is. That's just Fg equals gm1m2 over r squared. But make sure radius from the center. I cannot stress that enough. What if you're inside the Earth, though? What you're going to have to do is calculate the density of the object. Assuming it's a uniformly distributed sphere, you calculate the density and multiply it by the volume that is still beneath you. And how can you calculate the density? Well, that's just mass over volume. So if you're given the mass, you do that over 4/3 pi r cubed, because that's the formula for the volume of a sphere. And then let's say you're given a distance a is still beneath you. You multiply that by the volume 4/3 pi a cubed, because that's the volume of the sphere that's still under you. And that's going to give you the mass of the sphere that's still under you. Now you plug that mass into the law of universal gravitation. And you plug in a as the radius. Basically, what it's saying is anything that's above you does not get counted in the gravitational, because the different directions all counteract each other. But everything that's still beneath you gets counted, and so you have to calculate the mass of everything that's beneath you and plug that in, and the radius of everything that's beneath you. So it's a bit interesting to look at. And the graph of this, actually, you can make a graph of it. You might not need to, but if you have, it's always good to know. Let's say it's radius on the horizontal axis and force of gravity on the vertical axis. And there's a certain radius, r, that is the radius of the planet. This is, you have to split it here because there's two different scenarios. One is that you're inside the planet, the other is that you're outside. Again, this doesn't have to be for any for a planet, it can be for any solid sphere. And so when you're outside, we know it's going to be like a inverse function, specifically an inverse square because of this r squared. Now, what about when you're inside the sphere? Well, it's going to be linear. And the reason why is because there's this a cubed that you're multiplying by and dividing by a squared in this formula. And so it's just going to be times a, where a is the radius inside. And so this is going to be your graph. Now, what about a spherical shell? This is a hollow spherical shell, no mass inside. And so what happens is, when you're outside, it's still the same exact Newton's law of universal gravitation. What happens if you're inside? Now there's literally no mass underneath you. So there is no gravitational force. You might be thinking, well, what about this? You're very close to this side, but you're not as close to the other side. So shouldn't you be feeling a force this way? Well, if you zoom in a little bit, one thing that's interesting is you might be closer to this side, but if you look at it like sectors or if you look at it proportionally, you're closer to this side, but there's also less mass that's close to you. Here, there's a lot more mass, and it's farther away from you. And so those actually equal out. You can do the math behind it, but they cancel each other out. And so what would a graph look like that for this? If this is radius and this is force of gravity, this is the radius of the planet or whatever. Well, not a planet because it's a spherical shell. Again, it's going to be like this outside in an inverse square, but this is just going to be 0 the entire way through. Good stuff. All right. Now, that's about like probably half of the unit, like applying the gravitational formulas. Now we have to talk about like satellites and stuff. And so we're going to start off with planets and their orbits. So Kepler's laws. Kepler has a bunch of laws that you need to do. The first one is Kepler's law of orbits. And it's basically saying that all planets move in an elliptical orbit with the sun at one focus. Now, if you've taken honors pre-calculus, you would know what an ellipse is. It's basically a shape where the it's kind of like an elongated sphere, circle. I'm not going to give you the exact definition here, but it has a few properties like the semi-major axis, which is this, usually denoted with an A, and the eccentricity. And the eccentricity is basically a measure of how much of a circle is it. When it's 0, it's a circle. When it's 1, it's a parabola. So anything between 0 and 1 gives you an ellipse. So what it's basically saying is planets move in ellipses, not circles. People thought they moved in circles back then, and so this is pretty revolutionary. The second law, the law of area. So what it's basically saying is if you look at the area that a planet sweeps in a certain amount of time, it's always going to be the same. Same amount of time, it's always going to be the same. But you might be thinking, well, this is a very small area, but this is a very big area. Well, the thing is, if you're looking at the same amount of time, since the gravitational force is faster at this point, or sorry, the gravitational force is stronger, the object moves faster at this point. That's because you're just so much closer to the sun or the star. And so since it moves faster, it covers a greater distance in the same amount of time. Over here, it moves slower because the gravitational force is weaker, there's less acceleration. And so it moves slower. And so these two areas are actually equal. And Kepler is a very nice proof of it. I obviously am not going to go through it. We do not have the time, and you do not need to know the proof. But just know that the area swept out by the planet in the same amount of time, wherever it's in the orbit, is going to be the same. The final one's the law of the periods, and this one's a more formulaic one. What it's basically saying is that the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. A lot of people say cube of the radius, but since they move in ellipses, it's going to be the semi-major axis. And so the formula for it is t squared is equal to k times r cubed, or a cubed. A is probably more correct because it's the semi-major axis. But what is this value k? Well, some people write as kappa. It just depends. It's going to be equal to 4 pi squared over gm times a cubed. And that's going to be the law of the periods. Just, you should memorize that formula. You're probably not going to use it that much, but good to know. Good to know. Okay, let's see. Those are Kepler's 3 laws. You should definitely know that. And now let's get back into satellites. Now, when it comes to satellites, this is going to be mostly focusing on energy. And that is something we also have to talk about. Gravitational potential energy. Gravitational potential energy, we talked about that in work energy power, it's just mgh. But when you're looking at the universe and like beyond the Earth, there's a different formula. We know that the force is equal to g times m1 m2 over r squared. Now, we also know that the gravitational potential energy, or potential energy in general, is equal to the negative times the derivative of the force with respect to position. And so if you actually calculate the derivative, you're going to get u is equal to negative g m1 m2 over r. And the reason why it's negative, you might be thinking, well, why is it negative? We know that as you go farther from the surface of the Earth, shouldn't it be more positive? Well, yes and no. When it comes to just Earth-based gravitational potential energy, yes, it becomes more positive as you go away. Technically, it becomes more positive in this form. And let me explain why in a second. What this is saying is radius from the body, from the particle, from the Earth, whatever. And so what if radius is infinity? Well, you can't divide by infinity, but if you take the limit as r approaches infinity, you're going to get 0. What this is basically saying is at infinite distance, the potential energy is 0. And as you get closer, it becomes more negative. In other words, it starts to become, on the surface is very negative. And technically, that means that as you go away, it becomes more positive. It's still going to be a negative value. It's just going to be less negative, which means more positive. It's kind of confusing to wrap your head around the first time. But this is also funny story. Gravitational is a lot like introduction to electrostatics and electricity and magnetism, because the forces are very, very similar in terms of calculations, very different in terms of nature. But you're going to do similar stuff with electric potential energy and electric force and electric field and all that. So it's a good idea to pay attention to this unit because you're going to need it a lot for electricity and magnetism. Now, that's the formula for electric potential energy. Unlike, not electric potential energy. I confused myself. Okay, this is the formula for gravitational potential energy. Unlike gravitational force, when you have multiple bodies here, it's not a vector sum, it's a scalar sum. You just add up the gravitational potential energies. And that's because potential energy is a scalar quantity. Now, when you talk about potential energy, you can also talk about escape speed. Escape velocity. What that is the velocity required for a projectile to leave the planet, to leave the uh, Earth, whatever. And how can you calculate that? Well, you can use conservation of energy. What is the potential energy, the gravitational potential energy on the Earth's surface? That's U is equal to negative G M over R. I'm just using capital letters and lowercase letters to denote mass of planet, radius of planet. What's the kinetic energy? Well, that's what we want to find out. If we were trying to find the escape velocity, that means velocity has to do with kinetic energy. So that's what we want to find out. What the conservation of energy says at this point is the total energy at infinity is zero. The potential energy at infinity is also zero, but that's only if the kinetic energy at infinity is also zero. This means that conservation of energy, escape velocity is you want to go infinitely far, and so you just have to add this to the kinetic energy to get zero, and which means that kinetic energy is going to be equal to positive GMM over R. In other words, usually potential energy and kinetic energy are going to cancel in gravitation because it should be equal to zero, the total energy. Okay, now that we know kinetic energy is equal to that, we can do 1/2 mv squared and solve for v. You just multiply both sides by 2, divide by m. That's nice, it cancels out. So escape velocity actually does not depend on the mass of the projectile. It's all a property of the planet or body you're on. So you get v escape is equal to square root of 2 times gm over r. That's your escape velocity. Also memorize this formula, pretty important. You're going to get a lot of questions like that. So that's the escape velocity. Now that we covered all this potential energy and escape velocity, we can get back to satellites. There's a few other types of velocities and things you need to know. One of them is that the total mechanical energy of a circular orbit is going to be equal to negative gmm over 2r, where r is the radius of the orbit. If it's elliptical, they're going to be very similar. It's negative gmm over 2a, as you might expect, because a is the semi-major axis. And this is pretty important because now you know that it's not equal to 0 in this case. I said most of the time it's equal to 0 because you want to go infinitely far. But if you're in an orbit, you're staying in that orbit. You're not going infinitely far. And so this is the constant energy of that. So sometimes your potential energy would be some value. You can calculate it based on distance from the Earth or from the center. And then using that, you can calculate the velocity. And so if you actually do calculate the velocity, you're going to get the velocity of an orbit is equal to square root of gm over r. You can do the calculations for that, but you really don't need to. Like, actually, I would say that you should probably prove it on the AP exam or on the test, because you can't just show this equation, but you should know how to do that. It's very similar to what we did here. The sum of the energy should be equal to the total energy, and then you just solve for V. Okay, that's all nice, and that's basically all you need to know for gravitation. Lot of formulas you should memorize and just concepts you should know. So it's time to, I know this was a really long explanation, but better safe than sorry. Moving on to the practice problems. We have 7 practice problems today, starting with number 3 here. What must the separation be between a 5.2 kilogram particle and a 2.4 kilogram particle for their gravitational attraction to have a magnitude of 2.3 times 10 to the negative 12 newtons? That seems awfully small, but they're particles. I mean, that's a pretty massive particle. It really shouldn't be that massive, but it's still particles nonetheless. Okay, we know that force is equal to g m1 m2 over r squared, so you can rearrange it for r is equal to square root of g m1 m2 over force. Now you just plug in the values given. Square root of the value of g is 6.67 times 10 to the power of negative 11. I'm ignoring units for now. This is 5.2 and this is 2.4. And the force was 2.3 times 10 to the power of negative 12 newtons. And so if you calculate that, you're going to get 19 meters. That is the separation between them. And now you see why it's such a low force of gravity. They're small particles with relatively heavy masses, but they're 19 meters apart. And that's a lot of meters apart. All right. Moving on to number 10 here. This is about multiple particles. And so you have particle A has mass ma. particle B has mass 2 ma, and particle C has mass 3 ma. There's a fourth particle D is to be placed near the other three. So let's just arbitrarily say it's here. And this is 4 ma. So you're given all the masses in terms of ma. You can probably cancel that out at some point. In terms of this distance, what is the x-coordinate and y-coordinate of particle D such that the net gravitational force is 0? This is something you'll see so often on tests. You want to place something somewhere so that the net force is 0. Well, you just got to calculate stuff. Yeah, no, that's basically all of physics. You just got to calculate stuff. Okay, so let's find the individual force vectors for this problem. The force between A and B is going to be equal to G times MA times MB. MB is 2 MA. And so that just becomes 2 times GMA squared. And the distance between them is D, so D squared. Okay, what about FAC? Now that's 3 MA times MA, so that becomes 3 GMA squared over, this is 1.5 D, so that's going to be 2D squared. Or sorry, 2.25 D squared. And if you don't like fractions, you could actually simplify this a little bit to 4 over 3. 4 GMA squared over 3D squared. Sorry, if you don't like decimals, you're going to be stuck with a fraction nonetheless. Okay, now we also need to find FAD. Because this is the net gravitational force on particle A, and so you just need to find FAD. If it was in particle D, that would be a bit trickier because you don't know the distance here. This is actually relatively easy. I'm pretty sure you can still calculate it if it was net gravitational force on D, but why bother when we have an easier problem? All right, so what is FAD? Well, we don't know where D is, and so we just have to use a value or if you use a value like x or r between them, you could also solve for it. But I think an easier way would just be saying, well, we know the other two, so just add all them up, and that should be equal to 0. So what's nice in this case, not going to be in every case, is that AB is strictly upwards, and AC is strictly to the left. And so we can break AD down into two different variations. We know that the x forces have to cancel and the y forces have to cancel. You can replace this with 2GMA squared D over D squared. J hat, because we're using the I hat J hat notation gives us the vector form. So I hat is x-axis, J hat is y-axis. And this is actually minus 4GMA squared over 3D squared I hat is equal to 0. And we just have to solve for FAD. This looks very simple because now you just move everything to the other side and you're going to get FAD is equal to positive 4GMA squared over 3D squared I hat minus 2GMA squared over D squared J hat. And that just gives us the vector. No need to actually combine any vectors. This is a very easy problem, or not very easy, just easier than you're probably going to get. So that gives you your vector form for AD. We also know that FAD has a mass of 4 MA. So what can we do from there? Well, FAD is going to be, let's say it's x and y are the x-coordinate and y-coordinate of MA, of the fourth mass respectively. Well, it's nice that MA, the A mass, is at the origin. And so it's just going to be square root of x squared plus y squared is the distance between them. And since it's r squared, we can get rid of that square root. So that's the denominator. The numerator is going to be 4MA times MA. So 4MA squared. So 4GMA squared. Now, obviously, we can break that into the x and y components. If it's like this, we can split into x and y. And that's precisely going to be, you could do that, or you could combine this into one vector. If you were to split it into two vectors, you would have to know the angle, which you could do, but you can just combine this into one vector and then solve for it from there. If you were to Pythagorean theorem, add them together, this becomes 16g squared ma to the power 4 over 9d4 plus 4g ma to the power 4 over just d to the power 4. So if you multiply top and bottom of this by 9, you're going to get 36 here, and you're just going to get 9 here. And so together that's 52g ma to the power 4 over 9d to the power, and we have to square root that. Square root of 52 is 2 root 13. So that times gma to the power 4 over 3d squared, or sorry, gma to the power of 2 over 3d squared. What does that tell us? Basically not a lot, but if you were to use this to solve for x and y, you would get x is equal to 0.716d and y is equal to negative 1.07d. How would you solve for this? Well, that would be too much math for this video, but what you could do is for this 4 over x squared plus y squared is equal to 2 root 13 over 3d squared. And so now you can get x squared plus y squared in terms of d squared. And then you can simplify it using the angle, which is inverse tangent of y over x, and then break it into components. So I ran out of space on my screen, so I'm not going to go through all that. But this is just vector addition, and you can solve for it. So we're going to get a is 0.176d, and b is negative 1.07d. All right, time for number 17 here. What will an object weigh on the moon's surface if it weighs 100 newtons on the Earth's surface? So I'm going to pull some numbers out of nowhere here. I'm sure if this was on a test, you would get the values. If it's on a homework, you would probably have to search it up. But what we know is that we know the mass of the moon, we know the mass of the Earth, we know the radius of the moon, we know the radius of the Earth. And so what you can do is you can solve for the acceleration due to gravity on the moon with these values using Newton's law of gravitation. I'm going to skip that step a little. We're going to get the g value on the moon is, moon is equal to 1.67 meters per second squared. And so the weight on the moon is going to be equal to the weight on the Earth times the gravitational attraction on the moon over the gravitational attraction on Earth. That's also a formula you should probably know. It just means that the proportion is like this. The weight and the gravitational attraction are proportional to each other. And so if you just rearrange it, you're going to get this. Plugging what we know in, this is 100 newtons on Earth. That is 1.67 meters per second squared. And this is 9.81 meters per second squared, or 9.8. You're going to get approximately 17 newtons worth of a weight force on the moon. That's how much the object will weigh on the moon. How many Earth radii must the same object be from the center of the Earth if it is to weigh the same as it does on the moon? Well, we know acceleration due to gravity is equal to g times the mass of the Earth over radius squared. And so you can rearrange it to get radius is equal to square root of g times the mass of the Earth over the acceleration due to gravity. Now, we plug in what we know, mass of the Earth. Again, you would have to look that up. And you would plug in a of g is equal to 1.67. So you're basically finding out at what point is the acceleration due to gravity 1.67. And you plug everything in, you're going to get a radius of 1.5 times 10 to the power of 7 meters. So that's pretty far. Now, if you actually consider it to the Earth radii, though, because it's asking how many Earth radii, well, the radius of the Earth is actually pretty large. And so it's not that far. It's actually just going to be 2.4 Earth radii. So just radius Earth. So 2.4 isn't that bad. It's just this looks like a pretty big number because the radius of the Earth is also a pretty big number. All right, that was question 17. Moving on to 25 here. Solid spheres. Okay, we love these problems. Has a uniformly distributed mass of 1.0 times 10 to the power 4 kilograms and a radius of 1. With that, we can you basically use Newton's laws of gravitation. So we want to know the magnitude of the gravitational force 1.5 meters from the center, which means it's going to be outside. And so we can just use Newton's law of gravitation. That's going to be force gravity is equal to g times m1 m2 over r squared. And you just plug in what you know. it says m1 is m, which is not known, but we just have to find it in terms of m. We also know g, the constant. The mass of the sphere, it says, is 1.0 times 10 to the power 4, and the radius of the sphere is 1 meter, but we want to use the distance, not the radius, and so that's going to be 1.5 meters. You plug everything in, you're going to get a gravitational force of 3.0 times 10 to the power of negative 7 times m. So that's going to be your gravitational force at that 1.5 meter mark. At 0.5, that's inside the sphere. So what are you going to do? What we're going to do is find the density. That's the first step. Density is equal to the total mass divided by 4/3 pi r cubed. So total mass is 1.0 times 10 to the power 4 over 4/3 pi times 1 cubed. And so that's going to give you a density of 2.4 times 10 to the power 3 kilograms per meters cubed. Now, now that you have the density, you multiply this by the volume that is underneath you. So you use 4/3 pi. R is 0.5 this time, 0.5 cubed. And so you plug everything in, you're going to get a mass of 1.3 times 10 to the power of 3 kilograms. With that in mind, you can calculate the force using this same equation. So G's didn't change. M1 is M, which you don't know. M2 is now this new mass, unlike the previous mass. And then R is 0.5, unlike the previous radius. And so you solve for the force, you're going to get 3.3 times 10 to the power of negative 7 Newton per kilogram times m. I'm ignoring units in this case. And I know it looks like meters is the unit, but no, it's just m the variable. This is probably going to help. And now it's asking for an algebraic expression, so we just literally found this. Now we just have to undo what we did and just write in variables instead. So we know we found the radius, density, which is going to be equal to the mass total over 4/3 pi r cubed. Although we don't really need that, we just need to know the density because that doesn't change no matter where you are. And so you can just rewrite it as density times 4/3 pi r cubed, where r is the distance you're looking at. And we still have gm, this is the other m we're talking about, and you divide it by r squared. And so if you were to simplify it a bit, you would get 4gm, okay, I tried to do that on the fly. Let's collect the 4 and pi, and the 3 goes in the denominator, so 4 pi, and then g is a constant. We have this m, and we have an r cubed that cancels with an r squared, so that just becomes r, and that's over, and a row on the top, over just 3. And so that's going to be your answer. We also have an m. Now we can solve for the row, we can solve for g, and we can simplify this into one constant and just have something in terms of the variables r and m, but this should also work. All right, that was number 25 there. Number 39. This is escape velocity. And so all we have to do here is either use the formula or conservation of energy. We know the formula. So I say we can just use it, but on the test you have to derive the formula. That is an absolute must. You need to derive it from the conservation of energy equation. We know escape velocity is equal to square root of 2gm over r. And so what can you do with that? What you can probably do is just plug stuff in. Radius is 500 meters. And gravitational attraction is 3.0 meters per second squared. So we could just solve for mass from there, or we can say that acceleration due to gravity is just going to be equal to gm. So there's the equation for acceleration due to gravity that you can use. It's gm over r squared, because it's just the force divided by mass. And so if you were to plug it in into here, you can multiply both sides by the radius, and you're just going to get acceleration due to gravity times radius is equal to gm over r. Well, look at that coincidence, gm over r here. So escape velocity is going to be equal to square root of 2 times acceleration due to gravity times the radius. All right, nice. What can we do from there? We can just plug in values that we know. We know that acceleration due to gravity is 3.0. We know radius is 500 kilometers. Plug stuff in. We love that. We get that the escape velocity is going to be equal to 1.7 times 10 to the power of 3 meters per second. That's part A. Part B, how far will from the surface will the particle go if it leaves the asteroid with a radial speed of 1,000? 1,000 is not the escape velocity, which means it's going to come back at some point. Escape velocity is what you need to get to infinite space, right? So what can we do here? We can set a conservation of energy equation. At the ground, it has some amount of potential energy, U on the ground, plus it has some amount of kinetic energy on the ground. And once it reaches 1,000, once it reaches the height we want to find, it has some amount of potential energy, no kinetic energy. That's where it stops. We have formulas for all this. This is just negative gm over r. Negative gmm over r. Because it's potential energy. And then 1/2 mv squared, lowercase m. And that's equal to negative gmm over r plus h, because we're adding this extra height h to the distance. And so that's not too bad to calculate. We can cancel off the m first. And we also can replace gm over r with ag times r. And so this becomes negative ag times r plus 1/2 v squared is equal to, this we can't really replace, but what we can say is gm, if we turn this into an r squared, ag r squared is equal to just gm. And so this becomes negative ag r squared over r plus h. A lot of algebra here. I'm going to skip most of the algebra. You want to solve for height here. You know all of this. You know ag is 3. You know r is 500. You know v is 1,000. And you know all of these. So you just have to rearrange to solve for h. You would probably combine these. You would multiply both sides by r plus h and then divide by whatever you get when you combine these two. And then subtract both sides by r. Very messy equation. But if you solve for everything, you're going to get a height of 2.5 times 10 to the power of 5 meters. So yeah, I'm not going to do all the algebra because we don't have time, I don't have space. So better just show you how to do it and the answer. All right. Moving on to number 60. This is the last but one problem. This is also technically a conservation of... Oh wait, sorry, there's a part C, I didn't realize that. With what speed will the object hit the asteroid if it is dropped from 1,000 kilometers above the surface? Very similar problem. In fact, I'm just going to bring it back because you're going to use the exact same equation. You use this equation, it's kind of messy now. Whatever. You can cancel off the m, obviously. You can get to this equation even. And now it's actually simpler because we know height. All you want to solve for is velocity. So you know everything else. You just have to solve for velocity. And so now you just move this to the other side. You multiply both sides by 2 and take the square root. You're going to get an equation for velocity. And then you solve for the velocity, which is actually 1.4 times 10 to the power of 3 meters per second. Very similar to the escape velocity, but not quite. All right, that finally is it for number 39. Moving on to number 60. So also a conservation of energy problem, a very common type of problem you're going to encounter on the AP test and on the test. You have two satellites, right? And they're both on the same orbit, but they're moving towards each other. So there's going to be collision. You already know that's going to be conservation of energy. Technically also conservation of momentum, but I don't think you guys learned momentum yet. So you're stuck with energy. A, find the total mechanical energy of the two satellites in Earth system. So we actually know that the total energy of one satellite and the Earth is just going to be equal to negative g m Earth times m satellite over 2r. We know that from the equation. You should probably derive that. How can you derive that? Well, you can find... Well, honestly, you can just say this has some gravitational potential energy and some velocity, but if it was on the Earth, it would have this much gravitational potential energy, set those two equal to each other, and you would actually solve for the, the total mechanical energy. But yeah, you can also solve it other ways. but this is probably the easiest on screen. So you already know this. If you have two satellites, you just multiply by 2. And so this just becomes, the total mechanical energy is that. All right, what can we do from there? We can actually plug it in because it's asking us to calculate it, not as an expression. So we know G, we know mass of the Earth. It actually does it give? No, it doesn't give it to us. So we need to know that. Probably search it up, or on a test it'll give it to you. We know the mass of each satellite is 125 kilograms, and this radius here is 7.87 times 10 to the power of 6, and yeah, there you go. You plug all that in, you're going to get a mechanical energy of negative 6.33 times 10 to the power of 9 joules. Okay, that was part A. Part B says, if the collision is completely inelastic, so that the wreckage remains in one piece. Now, you didn't do momentum, so you're probably not going to know what completely inelastic means. But what it basically means is that momentum is conserved and energy is conserved. So what we know is we just need to solve for the total mechanical energy immediately after the the collision. Technically, since we know it's completely inelastic, it's going to be the same exact as this because energy is conserved in a completely inelastic collision. Now, you could also do it because you know that the kinetic energies are going to be equal to 0 immediately after the collision because they're just wreckage now. It remains as one piece. So it has no kinetic energy at the moment. And so now you just have to combine the masses and solve for potential energy. We know potential energy is negative G m E m over 2r because it's the formula. That's the energy at the orbit. And now we know mass is twice as much as it used to be because the two satellites are now one piece. And so you can cancel off. You get the same equation as here, and you get the energy that we got before. For part C, it says, just after the collision, is the wreckage falling directly towards the Earth or orbiting around the Earth? Well, it has 0 speed after the wreckage, and so it's just going to fall straight down. If it had the orbital speed required, then it would go in an orbit, but since it has absolutely 0 speed, it's going to fall straight down towards the Earth. So just fall down. All right. Almost done. We're on our last problem. This was quite a long video, but hopefully worth it. So also satellite problem, probably the most common type of problem you're going to get. You have two Earth satellites, this time not in the same orbit. Satellite A is at some orbit. Altitude of 6370. We also know that the radius is 6370. Satellite B is much farther, not to scale actually. This is 19110 plus the 6370 of the Earth. This is 6370, 6370. So yeah, we can't use the altitudes. We have to use the distance from the center. And so you're going to get a radius of A is equal to 12,740 and radius of B is equal to 25,480. And both in kilometers. Part A is asking the ratio of the potential energies. Well, UB over UA is equal to negative G m over RB over negative G m over RA. These all cancel out very nicely because the masses are the same. And so that just becomes 1 over RB over 1 over RA, which is just RA over RB. So these actually flip because RB and RA are in the denominator of their respective fractions. And so RA is this, RB is that. What's nice is that these numbers actually cause it to be a perfect 1 to 2 relationship. And so RA over RB, RA is 1, RB is 2, so that's equal to 1/2 is the ratio. Part B, what is the ratio of the kinetic energy of B to A? Well, what is kinetic energy? We know that the sum of the energies would have to be equal to 0, and since potential energy at the orbit is negative G m over 2r, that means kinetic energy has to be G m over 2r. Again, you might want to derive that a little bit, show how you got this equation, but now that you do have this equation, what you can say is, well, the ratio of the kinetic energy is KB over KA, is equal to GMM over 2RB over GMM over 2RA. Cancel off. The 2's cancel off. This again becomes RA over RB, which again is 1/2. Part C, which satellite has the greater total energy if each has a mass of 14.6 kilograms? Well, we know that the value of E, so the energy, which one has a greater energy? Well, that's just going to be the one with a smaller value of R, the smaller radius, because radius is in the denominator of all forms of energy. And so when you have a smaller denominator, you're going to have a larger value. So the larger energy would be the satellite with the smaller radius. And so technically, you would say that A has the larger magnitude of energy. However, we also know that energy is negative. Potential energy is negative. And since A has the larger negative value, this is actually a trick question technically, B has the largest energy. Even though it's a smaller magnitude, it's a larger energy because it's negative value. So let's say you have -10, -5. 10 is greater than 5, but -5 is greater than -10. And so what you're going to say here is that B has the largest energy. Keep an eye out on negatives and largeness of magnitudes and stuff like that, because that is one way to trip you up. Finally, part D, by how much. So you actually have to calculate the energy this time. So it's going to be EB minus EA. And we know the formula for the energy is this. So negative GMM over 2R. And so that's just negative GMM over 2RB minus, plus technically GMM over 2RA, which just becomes negative GMM over 2 times 1 over RB minus 1 over RA. Now, you want to calculate it. First, convert R's to meters instead of kilometers. When we were doing ratios, it was fine, but now we actually have to calculate a value. You need to, convert it to meters. You find both of these. You know the mass is 14.6. You know the mass of the Earth. It's going to give it to you in the problem, or you can search it up. And so you solve for all of this. You're going to get a delta energy of 1.1 times 10 to the power of 8 joules. That's your answer. All right, and that's actually it for today's video. We went over all of gravitation. So Newton's law of gravitation, multiple systems, gravitational potential energy, escape velocity, Kepler's laws, satellites, all that good stuff. And so, yeah, that's it for gravitation. This turned out to be quite a long video, but hopefully it was worth it. And so good luck for your test, and good luck for the AP test as always. And